Right, those were two questions that were rather harder than I thought. Or at least bits of them are okay. Question 1, modern physics. Albert Einstein and Niels Bohr provided explanations for the photoelectric effect and the emission spectrum of the hydrogen atom. Explain in detail the key underlying physics of each explanation and describe the fundamental physical connection between these two phenomena. And we have a lot of space to write on. Okay, so photoelectric effect and emission spectrum of the hydrogen atom. The question says, explain in detail the key underlying physics, not the history of it. Right, 1905 explanation from Einstein, Nobel Prize winning. That's not what they're wanting. So it's the physical physics of each explanation and describe the connection between the two. So that's kind of three questions: physical explanation, that physical explanation, and that connection between the two. So photoelectric effect, I think you have to somehow explain what the photoelectric effect is before you can just explain it. Diagrams, always good. So you've got light of frequency F, you've got a metal, so light comes onto it, electrons are ejected, but only if F is big enough. So Einstein's explanation of what was going on, so we've got this classic diagram: frequency of light, kinetic energy of electrons, and there's this cutoff here. So Einstein's explanation, the key thing was that the light is coming in packets. So light is photons. So each photon carries energy HF, where H is Planck's constant. So photon hits the metal. Each photon gives its energy to an electron. Okay. Question, is that enough energy for the electron to escape? If it's not, you're down in this regime. So the electron needs phi of energy, or energy phi, the work function, to escape metal. The rest goes to kinetic energy. So that would imply your energy of the electron, or your kinetic energy of the electron, is what you had in your wave packet minus what's needed for it to escape. That's basically Einstein's explanation. Explains that. It also explains why that it doesn't matter how intense the light is, you still get that. You just get, so if you double the intensity, you just get double the number of electrons. You don't get electrons of higher kinetic energy. So it explains why more intense light does not give more intense electron energy. I think for a question like this, bullet points are fine. Right, let's go on to Bohr's explanation of the emission spectrum of the hydrogen atom. So what do we mean by emission spectrum? That means if we heat hydrogen up, it's going to give off light, but at very specific frequencies. And we get this pattern of spectral lines. So F goes there. We get a spectral line pattern. Have I got that the right way around? That sort of goes like this, and you get a whole series of these lines. I think it's the other way, that's lambda, isn't it? You've got a minimum lambda you can go to. That's what it is. How do you get that? So here we're looking at transitions of electrons between energy levels. So more fundamentally than that is the fact that electrons can only exist, can only live in certain discrete energy levels. You can't have an electron in an atom with any old energy. So we might want to draw the diagram of our energy levels, which sort of goes something like that, and these get closer and closer together, up to the point there where they can escape the atom. So an electron can be in that energy level, that one. It can't sit there. And then, so your ground state of the hydrogen atom, electrons obviously sitting at its lowest energy. So if you heat up H, electrons can move to high energy levels. So we might get an electron up here. It can then fall to lower level and emits a photon of frequency given, well, your frequency is given by the energy gap is Planck's constant times your frequency. Well, here's your energy gap between the levels. And of course, given that there are only discrete levels, there are only discrete energy gaps possible. So only discrete delta E is possible, which implies discrete frequencies. That's basically what's going on. The key thing here, energy, the electron can only exist in certain energy levels. When it drops, it gives off a photon. It's really conservation of energy. So there's your photon being emitted. This frequency is determined by delta E equals HF. Okay, that's explanation. What's the connection between the two? Well, one obvious thing is our HF. So connection is both need to consider photons of energy E equals HF. Basically in the photoelectric effect, okay, so this isn't, you don't demonstrate this with hydrogen, you usually use a metal, but metals, they've got a series of discrete energy states, just like the hydrogen atom has. So to take an electron from here up here, it's going to take a certain discrete amount of energy to do it. So let's say in a metal your electrons are full up to here. Then to take them out is going to need a certain amount of energy. So certain amounts of energy needed to move electron. Of energy needed to get electron out of atom. So I guess we should say minimum amount of energy to get your electron off there, out of the atom, and then it's free to go. And there are some connections between them. It's really photons. This is what we're talking about, photons.